Cool. Let me load up my preview thing here. All right, folks. I guess we'll get started with today. As always, our students are mercenary and have no homework due, so we will no longer see most of you for the rest of the semester. But I'm used to it, and that's fine. And it's very motivating for your professor to go above and beyond preparing lecture. But it's always nice to see everybody, and welcome back. So in terms of reminders, the rest of this course continues to be straightforward. Essentially, you just need to finish your project. Any questions, comments, concerns about that? No? As a reminder, the course late days are not to be used for the course project. That's in the instructions very clearly. So if you run into a problem, I'm going to end up sending you to OGE or to S Cube, depending on whether you're undergrad or grad student. I can't. I don't have the capacity to read everybody's different issues and be a judge, jury, and executioner here. And plus, the reality is if you are running into problems at the end of the semester, you really should talk to somebody, and that person is not me. It's like somebody that's qualified to help you with that kind of stuff. So in any event, just an FYI, like if you email me asking for an extension, that's going to be the response. It's like, well, did you go talk to SQ? So you can save us both a little time by going ahead and doing that. But other than that, essentially your deliverables are pretty straightforward. I mean, essentially it's a write-up and a presentation, and I guess a draft. When is your draft due? Tomorrow. Good. So write your draft. And again, as always, so please follow the instructions, meaning that there is a template that you're supposed to use for writing up your projects. We do ask that you not go above the page limit, just keep it simple. All right, any questions, comments, concerns about that? Okay, so in today's lecture, I thought basically we would just finish off our discussion of optimal transport, and then next time we'll move on to some other mapping problems. So again, to kind of remind you the structure of this course, somehow we go from like very micro shape analysis to very, very global stuff, right? So we began this course by talking about curvature, which of course is like taking a little magnifying glass to a single surface. Then we talk about geodesics and paths, which are one-dimensional but larger neighborhoods on surfaces. We move out even larger by talking about the Laplace operator. And now we're finally talking about collections of geometric objects and mapping. And our first example of that comes from this optimal transport problem, where they're both at least embedded in the same space. And then what we'll start to do to wrap up this course is talk about correspondence problems, where you have two different shapes and you're trying to map them onto one another. Right? So we start very local and we zoom out to very, very global. So essentially, to give you a little bit of a reminder from our previous lecture, the object that we've been studying is this optimal transport problem, which involves being given two different probability distributions on the same domain. So the running example we had, if we go back a few slides, somewhere, oh no, is basically here, where you kind of have two distributions sitting on a space. So here it's like a one-dimensional space, and your distribution is some pile of sand sitting on top of it. And essentially the optimal transport problem asks, what is the minimum amount of work that it takes to transform one of these distributions into the other, where work is measured by the product of distance traveled with mass that you pick up. Right? And so that leads us to this sort of generic linear programming formulation, where we look over all possible measure couplings, which remember are functions pi of x comma y, which tell me how much stuff I can pick up at x and drop off at y. Over all possible measure couplings, which one minimizes this particular notion of work, which is a double integral of basically the mass that you pick up, right, which is this d pi quantity multiplied by some cost of moving things from x to y, right? So for instance, I think the most intuitive one is distance, but as we found out, for example, distance to the pth power is an interesting kind of alternative, where for any p larger than or equal to 1, this quantity has a triangle inequality associated to it if we take the pth root, and this thing is called the Wasserstein distance. Or you could imagine other situations, like maybe there's economy of scale, like if I drive more than 100 miles, it's actually like the cost of driving an additional 100 miles isn't as big because I've loaded everything into my truck or something like that. So there's a lot of different versions of this problem, and people study the bejesus out of it. So for example, in economics, it's very typical to study what is the structure of an optimal transport problem given a very particular choice of cost that comes from an economics problem, right? Which is a totally reasonable setting. People in linear programming worry more about like how to solve this thing in practice, often in the discrete case, and many things in between. Right? So that's our basic high-level setup, and then we ran out of time. Okay, so that's our story so far, and we covered a couple different formulations of this problem. I should pause. Any questions about our basic setup, the object of study, and transport distance, Wasserstein distance, all that good stuff? Cool. Yeah, I mean, I think that the basic problem is quite intuitive. The only problem is that, like, it's not often solvable, right? I mean, we're looking for, in general, if our probability distributions are, like, just smooth functions on the plane, then we're looking for a matching between every possible pair of points on the plane, which is an even bigger infinite dimensional object than we started with. and so from a computational perspective, you know, the story doesn't begin and end at linear programming. It's much more complicated than that. Right, and so we talked last time about one or two cases where we can actually solve this problem. So for instance, maybe our problem is fully discrete, meaning that our mass is an empirical measure. It's like concentrated in a few discrete locations, in which case we reduce to a linear program. We know how to solve that. Or the slightly more surprising and special to optimal transport case was a semi-discrete transport, where one of our two measures is discrete and the other one is smooth. And remember, in that case, we argued you could still solve this problem, but you have to have kind of a funny change of variable. Like you're looking for Voronoi cells that kind of describe the region of the blue distribution that gets assigned to each of the red points. So we'll dig into that a little more later. Okay, so that's our basic problem, and hopefully we understand the basic construction of these transport problems. One of the really beautiful things about optimal transport theory and these distances and formulas and so on is that somehow there are a lot of different reasonable notions of divergence between probability and measure you could cook up that all try to combine probability and geometry in different ways, right? And one of the kind of funny historical artifacts of this domain is how many of these have been proposed in different spaces, and then later on people realize it's just the same quantity again. Like somehow there's some huge equivalence between all these different intuitions you might have, whether they're drawn from physics or geometry or whatever else, that end up leading you to the same path. Which is also quite convenient if you're a theorist in this area, because it means that there's like a lot of different formulas for the same thing, and you can pick and choose any one of them when you try to prove your theorem. Of course, there are many different formulations and places where transport came from. One of the original ones was really in this discrete case. So you can imagine a universe where C is a discrete metric space. It's just finite to begin with, in which case this really does have a triangle inequality. And you can show that exactly when this distance cost D has a triangle inequality, then this function OT does as well. But again, this is another kind of way of understanding that essentially what you're doing here is you're lifting transport distances from distances on a base domain, like distances between points X and points Y, to distances between distributions over that space. Does that sentence parse when I say that? Hopefully we kind of get what I'm saying by now. Incidentally, if you want a good kind of fun theoretical exercise, when I say fun, I mean like actually kind of hard, is to prove this thing in the shaded gray box, which is specifically just for this linear program. If this matrix C has the property that like, it has a discrete triangle inequality, so like Cij plus Cjk is less than or equal to Cik, and the diagonal is 0, that this quantity, OT, has a triangle inequality on vectors VW. There's your fun theoretical exercise. Kind of a fun footnote is that the original paper that proposed this thing was called the Earth Mover's Distance. They were one of many papers that did not realize this is the same as this classical optimal transport problem. And at least according to the authors of the second paper I've referenced here, the proof of a triangle inequality is completely wrong. But these guys went back and fixed it, so life is good. There's still order in the universe. It really is a distance metric and so on. This was originally proposed for like image retrieval. So like, you know, I can maybe take an image and represent it as a set of like interesting key points, maybe decorated with some information. And now this gives me some distance between two images by like matching key points together or something like that. That was the original application in computer vision. Yeah, so anyway, if you want a spoiler alert and you don't feel like proving this theorem on your own, you can read this thing down here. It would be, I would say, slightly more difficult than the hardest homework problem in this class to prove such a lemma, but you all have the machinery to do so. It's just like a bunch of reasoning about an optimization problem. But this is only one of many formulas for the same thing. So just out of curiosity, how many of you have encountered linear programming before, like in another course or something like that? Many of you have, including some that haven't raised their hand, because I literally helped them through one of these courses in the past. So in that case, we know if there's one thing that we do to a linear program, what is it? Like, what do we know about linear programming? Take the dual. It's like the thing that you were programmed to do in linear programming, right? Anytime you see a linear program, you wake up in the morning, you brush your teeth, you're an operations research person, so I assume this is what you do all day, and you look at a linear program, the first thing you should do is compute this other linear program that somehow has the same optimal value, right? And moreover, there's this beautiful theory in linear programming and convex programming more generally, which says for any one of these things, there exists, for every minimization problem, there exists another maximization problem with the same value. And at least for linear programming, you can kind of read off the solution of one to the other. Hopefully that story maybe sounds familiar. So in this case, the dual of the optimal transport problem is really, really nice. So optimal transport, even if you put it in the original form with all these integrals, it's still kind of like a linear program. Do we see that? That like, there's, what is our variable? It's this pi. Remember, like, what does pi satisfy? It's basically just inequality constraints, right? That like, it's the rows sum to a particular value, the columns sum to something, and it's positive. And if you look at the objective function, it feels complicated, but at the end of the day, it's a product between pi and a constant. This is linear in pi, And so, just the same way that there's linear programming duality, there's also duality in this sort of infinite dimensional case. And in fact, one way to kind of guess, I won't say prove because there's a lot of theory that has to go into justifying duality, but to kind of guess the dual formula is to like start with the discrete one, do the calculation you've done in your linear programming class, and then just kind of like squint, like turn sums into integrals. And indeed, you will get to the right formula. And if you open up like Villanese textbook, you'll see a nice proof, which by the way looks basically like linear programming duality, just kind of like in souped up measure theory language. Which leads to the formula down here. So it's a really interesting like kind of pair of formulas that give you the same optimal value, and it's totally bizarre to figure out how they're related to one another. So remember that the linear problem for optimal transport discretely, we've written it in many different ways. Like in your homework, I think it looks something like this. T, take the rows sum to some value. I don't know, P, and the columns sum to some other value, like that, right? Then if you're trying to do linear programming duality, what do? You have to introduce the dual variable for every constraint in your linear program. And so you end up with like one here and one there. And so if you're familiar with linear programming duality, what do you know? So you know that basically there's one variable in your dual for each constraint in your primal, right? So in this case, how many constraints are there? We kind of count. Yeah.
Like number of columns plus number of rows.
Yeah. So in particular, like let's say that I have an n by n matrix C, right? Then there's essentially like 2n constraints here, like that. Okay. So what does that mean? That means in the dual linear program, I'm going to have 2n variables, right? Because like kind of variables and constraints swap roles in duality. Now, how many objective terms do I have here? Like in this linear expression, well, how big is T? How many rows are in T? N. How many columns are in T? How many entries are in T? Thanks, team. One more time. Thanks. Now the people in the back. N squared. Everybody in the back. You're not going to do it, huh? No, we're on our phone. Okay, so, right. So, in particular, we have 2n constraints here. We have n squared terms in our linear objective function. So, at the end of the day, if we look at our dual program, we're going to get the following. Right, so essentially you'll get the inner product of phi and p. Sorry, I'm like glancing. The inner product of psi and q, such that phi I plus psi j is less than or equal to Cij for all I j. Okay. If you kind of look at the problem that we wrote on the screen, you'll see that they're basically the same. All I did was, anytime there was a sum, or a sum here, there's an integral there, and vice versa. Incidentally, if you're wondering how optimal transport theorists do this kind of stuff, this is secretly what they do on their scrap paper. You just do your linear programming proof, and then you don't tell anybody, and you write fancy integrals. Okay, that's really what's going on in this domain. And there's a reasonable question, which is how to interpret this formula here. Now, for one thing, there are advantages and disadvantages to both formulations, right? Like, you could imagine that, generically speaking, one of these is not somehow easier or harder to solve than the other, right? Like, if you run standard algorithm for solving these, it, in fact, it's probably solving them both at the same time. Like, you kind of squint at simplex algorithm or something like that. The advantage here is that you don't have very many constraints, but you have a lot of variables, and vice versa on the other side. But there's a little bit more that you can say, because in typical application of optimal transport, this C thing isn't just a generic matrix, right? It has a lot of structure. Like, it has triangle inequality, or maybe it has pairwise distances between points or something like that, which means that maybe in practice I actually don't need to store C at all, right? So for example, let's say that Cij is really just equal to the distance from xi to yj for some fixed set of points, like that, then maybe I really never need to store a quadratic number of values. I have a quadratic number of constraints, but I never need to keep them in memory all at the same time. You see that? And this is our little toehold into cooking up different algorithms that might work better in one case or the other. That we can just make use of tiny amounts of additional structure beyond the just generic linear programming story that make our problem a lot easier to solve. Now there's a different question you could ask, which is how should I interpret this formula here? This is always something you should do. Every time for those of you who haven't taken a linear programming course, there's basically two things. You brush your teeth, you take your favorite linear program, you compute its dual, and then you need to step back 15 feet, roughly, where Leticia is, and you need to look at that linear program and say, what is that telling me about Lich? Why should these two quantities be equal to one another? In this case, there actually is a really nice, kind of economics way to interpret the relationship between these two formulas. Does anybody know this story? I always get it wrong, so I'm happy if somebody wants to raise their hand and do it for me. So it has to do with the difference between the consumer and the sort of salesperson. So if I understand, if I get it right, you can think of the primal optimal transport problem, where it's minimizing cost, right? This is a consumer perspective. I want to minimize, the amount of cost it takes for me to move my mass around. So maybe somebody's charging me C dollars for every unit of mass I move from X to Y, and that would be what this linear program is trying to do. Does that make sense? On the other hand, I guess the maximization problem here, by the way, this word max, in theory you need to justify, right? If you want to be wishy-washy, you put soup here, but it does happen to be a max. The max problem is a pricing problem. So it says, let's say that I set up a shipping company, and I want to maximize my profit, right? And what I'm going to do is I'm going to charge you, if I drop something off at X, then then I can charge you $5. And if I pick it up at Y, then I charge you psi dollars. Well, I want to maximize my profit, right? Which is roughly this, right? Because this is my pickup cost plus my drop-off cost, or the other way around, sorry. But I need a constraint, which is that my consumers are smart, and they know that if I charge you more than it costs for them to just drive, they might as well drive, right? And so if you think of C at XY as the true cost of moving something from X to Y, then what is this saying? It's saying well, I want to maximize my profit in this particular model where there's pickup and drop-off cost. But I never want it to be cheaper. I don't want some competitive company to go in and underprice me by essentially doing something at cost, which is C of XY, right? And that's really what this dual linear program is saying. So anyway, it's kind of funny that there's this nice duality between these two perspectives, but indeed, at the end of the day, they lead to the final, the same cost value. And then by complementary slackness, one thing that you can figure out is when this inequality here is an equality, so I optimize for psi and phi, when these things sum up to C, those are exactly the points x, y where pi is non-zero. Those are the places where your transport problem would happen. Yeah. So there's a really nice little theory that links all these things together. I think this is one of the cleaner examples of linear programming duality that you can encounter, and it's like very easily interpreted. Any questions about that little story? It's kind of a nice one. If you're like used to, you took a linear programming course and you're a little rusty, you should get out some scrap paper and do this dual, at least in the discrete case. This is like the classic example of linear programming duality, and I think it's kind of an illustrative calculation because it tells you like how to recover variables from these two pieces. Incidentally, you all secretly computed this linear programming dual on your homework. So in that case, you added an entropy term here, but then if you recall, you ended up optimizing for 2n variables, right? And those are exactly the dual variables in this problem, up to exponentiation. So everything fits together. So already, I mean, I don't know, like if you step back 100 feet, maybe if you've seen the new programming duality, you're not so impressed. But like, it's already kind of cool that you have these two extremely different formulas that agree and both give you the same transport problem at the end of the day. In case this isn't enough, it turns out there's all kinds of other theory that gives you other kind of interesting formulations. So here's one which is extremely famous. I'd really like to share it with computer science students because this formula goes back to Benjamin Brenier. It's actually and fairly recent, even though it's the foundation of a lot of transport theory. When I say recent, I mean like recent in math terms, not in machine learning terms. But in any event, there was this really interesting observation that optimal transport can be linked to fluid dynamics, which is totally bizarre. And so there's this beautiful formula here from Benjamin Brenier. Let's see if we can interpret it a little bit. And essentially it says, I'm going to put a lot of structure in my cost function. I'm going to assume that C of x comma y Sorry, Marcel gave me this nice box of chalk, but I feel guilty opening it. So tiny. Oh, look at that. It comes in like a little thing. Are you sure? Okay. There's like a chirality to this chalk, right? Isn't there some way you're supposed to use it? I don't know. We'll just start writing and see what happens. Okay, so right. So remember what W2 is. What nice talk. Right, so this is an F over transport plans of this particular integral, right? Which is, I guess, because it's W2 squared, it'll be the distance from x to y squared. And again, if you're not used to this fancy double integral notation, it's perfectly fine to think of this as just like xi minus yj times pi ij. Like that's completely fine here. This is just a continuum limit of the same thing. So, right, so essentially what Benjamin and Brenier do is they totally reinterpret the problem. They say that I'm going to think of mu and nu, or sorry, I guess I switched to rho naught and rho 1, as the density of a fluid at 2 points in time. Okay, so think about like a gas. Like I've got this entire room here, and then I release some gas over here, and then later on I observe it somewhere else. And of course there are many, giggling, geez, now you wake up. You're like staring at your laptops, and then I say, never mind. So I have, right, so here's me, and here's my gas, and then I observe it at some other point in time. And essentially the optimization problem I'm trying to solve here is to explain the motion of the gas from one point at a time to the other. And of course, there are many things it could have done. It could have like spread out in between and then converge back at that point. But I've got this weird boundary value problem. And essentially, over all of these things, there's some matching which minimizes kinetic energy. Okay? So in other words, here I'm going to think of like there being an animation problem where there's a density function rho t, which gives me the density as it changes over time. And I'm going to prescribe rho t at time 0 and time 1. And now, the only constraint I have at rho t in between is that it integrates to 1. It's just some time-varying density. And now I want to explain its motion. So here's what I'm going to do. I'm going to say that v of, I guess you can think of it like x comma t, is the velocity of my fluid, like that. Okay? And then rho of xt is like the density. So first of all, I need a constraint that links these two things together, right? I need to actually make a constraint saying v is the velocity of rho. Does anybody know the name of this particular equation from physics? There's actually two different ones you could use. So one of them is called the continuity equation. Really interesting. So you just don't take PDE anymore. Sometimes called the convection equation by physics, which says the following. Like that. So, which hopefully is both on the board. Up to sign. By the way, the sign of the d rho dt doesn't matter, and otherwise I've gotten it wrong here. So it really should be a minus, and let's think about why. So again, what this thing is saying is v is the velocity of rho, and you can kind of intuit this. So what is divergence measure? Div. This is a div. It's measuring how much a vector field kind of spreads out, right? So if v, like the velocity, is spreading out, what do I expect to happen to the density?
Decrease.
What's that?
Decrease.
Decrease, right? Because v is like smearing out the density function over a wider amount of space. And that's essentially all the continuity equation is saying. It's just saying that if v is spreading out, then dv dt is negative, and vice versa. Right? Physicists have all kinds of fancy rules for it, but this is an easy way to remember. Okay, so this is enough of a constraint. Also, we have just that rho of x0 is identically equal to rho 0 of x, and similarly, rho of x1 is identically equal to rho 1 of x, like that. Okay, so I have this boundary value problem, and I've prescribed it at 2 points in time. So, yeah.
Is it dv dt or d rho dt?
D rho dt, thank you. As usual, I say one thing and write another. Thank you. Otherwise, this wouldn't make sense, because it's a scalar and a vector. Thank you. Okay, so these constraints together just say that v is velocity of rho, and I know rho at 2 points in time. And then essentially what Benoit Bernier observed, which is kind of cool, is you say, well, I can now, like, it's kind of like a computer animation problem. You see that? Like, I have rho at these 2 points in time. I have these two objects I can work with, like the velocity or the density, and I could choose animations that do different things. What Benoit Bernier showed is that there's a very particular objective function, which is 1/2 rho mod v squared, like that, integrated over space and time. Right? That's what's inside of the integrand there. Does this formula look familiar if you've taken a physics class?
Yeah.
Can you tell me what it is?
It's the wave function. It's the expected value for an operator on a wave function.
Okay, it is that, but there's also an even simpler name for this thing. It's mass times velocity squared. Kinetic energy, yeah. It's also whatever Matthew said about wave functions. But this is, I think, a simpler one, which is this is the total amount of kinetic energy that it takes for me to move rho kind of along that path from one configuration into the other. Okay? So this is one of these universes where, like, I could have been an animation person and cooked up this optimization problem in a vacuum, like not known anything about optimal transport. So like this feels like totally reasonable objective function. That's because it is. But then it turned out that Benoit Bernier in 2000 proved that it's actually exactly the same as the transport problem. This is like the optimal objective here is exactly W2 squared. The proof of this theorem is boring, which is it's actually kind of depressing how boring it is. So here's what they do. And again, unfortunately, in our like one lecture, we don't get to I would love to teach a whole class on computational transport, but Philippe already does that in math forever. You look at the optimal transport map pi, right? So you get this matching from time 0 to time 1, and then you just move mass along straight lines from every x to every y in that map with constant speed. And literally the proof of the Benoit Bernier theorem, even though it looks so pretty, is just that that object happens to satisfy the optimality condition here. I don't know how they guessed this when they started. It's kind of shocking. But in any event, this gives you a completely different way to discretize and work with these problems. Because this looks an awful lot like things that we've done on meshes in this course, right? You see vector fields and velocities and so on. And so there are these two completely different classes of computational algorithms we're solving transport problems. Some that kind of look like linear programming and are optimizing for that pi object, and then others that look like fluid dynamics and are optimizing for rho, and at least in the limit, they all converge to the same quantity. Now, there's some interesting questions kind of adjacent to this one that you might ask. First of all, one thing that is a little bit annoying, linear programs are convex. This quantity is not. This is cubic in your unknowns. Do you see that? It's the product of rho and v, right? And in general, like xy squared is not a convex function. And that's a problem, right? It's very hard to, like, you could imagine a universe where you could find like a local optimum of this problem. However, that turns out not to happen. And the theory here is just so beautiful. I just love this area. So here's what you do. And by the way, the constraints are also not convex here, right? Because you have div of rho v, so that rho v is a product of variables. However, you can define a new quantity. I believe conventionally you call it j, which we're going to call rho v. Now, if rho v squared is kinetic energy, this thing is mass times velocity, which is momentum. That's right. Isn't it nice? All this stuff is just physics, right? So here we're going to optimize for, instead of v, we're going to optimize for j. Okay? So in that case, what you'll find is the following. So you've got rho v squared. If you substitute in, you'll get j squared over rho, like that, which feels a little uncomfortable. Like division is something we don't like, kind of. But notice the constraints are a lot nicer, right? Now you just have div j is equal to minus d rho dt, and rho 0, rho 1 are prescribed. Yeah? But here's a really interesting fact about life. This function looks nasty, but it's actually convex. So just generically speaking, mod x squared over y is a convex function jointly when y is greater than or equal to 0. If you feel like proving this lemma, there's the painful hard way and then there's the easy way. I'll let you try both at home. So the hard way would be to compute the Hessian of this thing and then like kind of check. You can do it, it's just ugly. The cleaner way is to notice that this kind of looks like the determinant of a 2x2 matrix. And so you can kind of reduce this problem to like a 2x2 semi-definite program. But either way, essentially this is actually a convex program for rho and j jointly, which gives some clue as to like that this thing can't really have local optima. Like hiding inside of it is actually a perfectly nice convex structure. And moreover, I think most of the algorithms you see in practice for solving this problem do this change of variables first. Yes?
How can y be equal to 0?
It can't. Yeah, this is a fantastic point. So here's what ends up happening. If you can do this in practice. Like you can play this CVX tool that you guys have played with in your homework actually has this function in it. And sometimes you will get rho equal to 0. So the way that this ends up getting justified is if you take a sequence of things that approaches the minimizer of this, then what will happen is that j will approach 0 faster than rho. And so it turns out you can get rho equals to 0 so long as j is also equal to 0. Yeah. Which kind of makes sense, right? What it's saying is that if there's no mass, you don't have to have momentum. Yeah. Any other questions? This is a fun problem, and it's really beautiful. I think in the history of transport, it's kind of cool. Also, like as a snarky computer scientist, I like to point out this research paper because it's in a computational journal. Like, this is a foundational formula in the theory of optimal transport, and it was originally designed because like Ben and Brunier were like, well, I want to solve this numerical problem, and it's really big, and here's this cool equivalent thing I can do. And then theorists went back and proved a bunch of theorems about it, but like that came later. Kind of an interesting thing you might notice about this formula, and then I'll stop just being excited about it. So remember when we talked about computing geodesics in this class? What did we do? We derived our formula by cheating a little bit. We defined this other object called the energy of a curve, and we worked with that instead. Remember the energy, geodesic distance or distance where the length of a curve, it looks like that, right? And then, but this is kind of annoying to differentiate, so we proved this little lemma that a minimizer of this is the same as the minimizer of that quantity, which is the energy. Well, if you kind of squint at the Benjamin-Bernier formula, it kind of feels similar to the energy of a curve in the sense that like there's certainly a velocity squared sitting inside of there. You have this curve, which is kind of like the time-varying distribution. And in fact, the Benjamin-Bernier formula is the tip of a really cool iceberg, which is you can think of there being this abstract manifold of all possible probability distributions over a domain. This is an infinite dimensional manifold. It looks like it's two-dimensional because I drew it on the board, but it's actually infinity. And so what this thing is doing is it's saying, like, I have like this Gaussian distribution and I have some other Gaussian distribution. And when you saw the Benjamin-Bernier problem, it's actually computing geodesics, computing a shortest path in a really weird metric. So in any event, this little theory here ended up being really foundational to putting an entirely new kind of geometry on a set of distributions that looks like Riemann, right? It looks like you could ask, like, what is the curvature of probability space when you get into this domain? If you're wondering, the answer is it's really scary. But in any event, if you like this kind of stuff, the phrase to Google for it is kind of cool. It's auto-calculus, which essentially is an entire calculus on a set of probability distributions, where they say, like, well, what is the tangent space of probability distributions? It's like the set of functions that integrate to 0, because you can add those differentially and not change being in that domain. And so essentially all you're missing is an inner product, and I'll let you guys kind of reverse engineer what the inner product here has to be. Right, so anyway, it's a bit of an advanced digression, but I thought it's worth, like, these are some interesting keywords to think about in Google for later. Yeah?
Did we gain anything computationally?
Yes, yeah, that's a great question. So like why would you care about this computationally? So there's sort of two different regimes where people solve these transport problems. One of them would be in extremely high dimensions, where your probability distributions maybe aren't so complicated. And the other is in low dimensions, like 2. So like, for instance, like if I'm trying to interpolate between 2 images or something like that. So in the 2-dimensional domain, you could imagine a case where rho is an extremely detailed function. Like, for instance, I have a pixel grid, and at every pixel on the pixel grid, I have a different density value, right? Then if I use the linear programming formulation here, then I need this variable pi is going to scale like quartically in the size of my domain. It's really, really big. And so one of the the original motivation here was to leverage this change of variables to make this problem more tractable computationally, because now you're keeping track of a time-varying rho. So like you have the product of x and t, rather than this sort of quartically growing pairs of x's. So there's an interesting numerical analysis question hiding there, which is how many t's do you need? Because if it's a lot, then you haven't saved anything. But empirically, it seems to be lower. Like the motion that you get from this transport problem is really boring. It's like a straight line. And so somehow you don't need that many t's to resolve it. So that was the original application. These days, I think you generally see this in, like, for example, if I'm on a curved surface and I want to solve this problem, then C is actually quite expensive. It's like geodesic distance, right? So if I wanted to solve this on like a triangle mesh, what would I have to do? I'd have to first compute the geodesic distance between every pair of vertices on my mesh, and then solve this linear program, which is expensive. It's in fact expensive even just to store that. Whereas this thing like doesn't require any of that. It's actually just built out of machinery we've already done in this class. Yeah. So that's the basic difference. On the other hand, in extremely high dimension, like putting a grid on 50-dimensional space is not a thing you want to do. So then you have to go back to the drawing board. Then you're stuck using other stuff. Yeah, great question. Incidentally, the other reason that some people like this version, I should hold on to this chalk. I shouldn't leave it behind. Is that you can also imagine regularizing it in different ways. So like, if you put on your computer animation brain for a second, you say, great, well now I have access to this time-varying rho. Maybe I'm just going to add some objective terms here to like make it have interesting motion. Like maybe I add some curl to V by like, promoting it in the objective or something. And there's some like fun modeling that you can do there. One very simple thing that you can do is simply regularize it by adding, I think it's on this side, like alpha times the Laplacian of rho, like that. And it turns out that if you do this, you get precisely what you did on your homework. You get entropy regularized optimal transport, where alpha is the amount of entropy you add, or proportional. I never get it right. thing here, the keyword to Google for is Schrödinger bridge, is the phrase. And now having a bit of a rebirth in machine learning literature because it's like connected to these diffusion models, right? Like this is a boundary version of diffusion. Yeah. So everything links together here. Okay, so that concludes the initial part of our story, namely that there's just like 5 billion different ways to write down this same formula for optimal transport, which is fantastic because depending on your application, you have like many different formulas to draw from in terms of how you're going to actually solve this problem in practice. Does that make sense? Any questions so far? I think it's a fun space. It's fun just because there's so many different sort of theories you could throw at it. The next thing I thought I would do is really quickly give you a grab bag of the kinds of problems people solve with this machinery. And there's many. In fact, including in my research group, I think we're all kind of guilty of this sort of goofy phenomenon that's happened where, like, you know, every time you see a KL divergence in your everyday life, you start asking this question, which is like, well, maybe I could drop in a transport distance instead and like improve somebody's model. And indeed, there is this sort of big research push, certainly in the sort of, I'd say, early 2010s, roughly when I was getting my PhD, so I was a lucky guy that way, that really did try to like just kind of insert different, see why Westerstein distances or optimal transport problems might be valuable in different settings. So essentially what we're going to see is that there's sort of two different key ingredients that go into all these applications. One of them is the ability to solve transport problems. We actually haven't talked too much about how to do that, but you have at least one from your homework, and we'll come back to that. And then moreover, these days, differentiating into the result of the transport problem is also valuable. So for instance, maybe I have this W2 quantity, and what I really want is some quantity like dW2 d rho. I'll put in quotation marks because that's infinite dimensional. And once I have that gradient, then I can say like minimize the transport distance between these two objects or something like that. And really the gradient is no harder to compute than the problem itself. You just have to differentiate through it. I say as if that's easy to implement. Moreover, there are some nice properties you can have. For example, this functional that inputs two measures and outputs the transport distance is itself convex in a certain space, and so there's some nice things you can say. So let's see some quick examples. The obvious example is in operations and logistics, where they actually have transport problems. And of course, this is the basic formulation that gets used in that domain. Linear program solvers for optimal transport really have their history here, where like I have a graph or a network or a pairwise distance function, and I really do want to like move my product around. And indeed, that's where this theory has its history. But the applications go farther than that. So for example, one of the ones that's quite popular recently is in natural language processing for document retrieval, these sorts of tasks. So here's the basic conceit. This is something they call the word movers distance, which is cute because transport is the Earth movers distance, where essentially recent models, they like word to vec and so on. What do? They essentially take the English dictionary and then they map it into Euclidean space. So every word is really a point in some space, and like maybe nearby words have nearby location. Now, how one engineers that particular embedding is a whole can of worms. So that's certainly not in the scope of this course. But if you buy that, then what is that doing? It's like putting a geometry on the space of words. So if a single word is a point in space, then what is a document? Well, assuming that none of us read documents linearly, like all we care about is the collection of words in our document, then a document would be like a little cloud of points in word space. Again, obviously some meaning is lost when you represent a document that way, namely the order of the words in your document. But very coarsely, you get some idea of what a document's about by if I took all the words in my document and just sorted it, I'd probably still have some rough idea. So, what do these folks do? You can also kind of guess when this paper was written based on the example they've chosen. You view a document as a collection of points in space, and now you can compare it to other documents by computing the transport distance between these things. So for example, document retrieval is a very common task in the legal profession. So I have some maybe giant thing that comes out in discovery, or this huge pile of documents that's coming from Enron or whatever company I'm trying to prosecute, and now I'm trying to search for things that are discussing a similar topic to the thing I just read. Then these are the kinds of tools that they use to cut through a big corpus and find things that might be relevant, right? So you can sort based on transport distance. If you are an algorithms PhD student, I know there's at least one in this course, an interesting question you might ask is, how do you make this efficient? Right? So we spend a lot of time talking about how to solve a single transport problem efficiently, but let's say I have a huge collection of documents and I'm going to have to do it many times. You might ask, like, can I amortize computation of this distance over many queries? And I think this is an understudied problem. This is not something people think about a ton. In registration and reconstruction, optimal transport also shows up there. So this paper from Jean Ferry and colleagues in 2017 is a nice example where maybe I'm trying to align different medical image scans. Then I can use optimal transport as a nice cost function for that, right? And there's sort of two different ways that I might do this. So like if I have two different scans of the same medical image, if they're in the same coordinate axis, like think about, you're inside of the MRI and you haven't moved around too much. I take two scans of your brain and I want to align them to each other. It would make perfect sense to solve a transport problem to kind of map one onto the other. There are also cases where transport makes no sense and you have to be a little careful. So for example, if I take, a scan of my body, take a scan of somebody else's body who's like positioned somewhere else in this room, then transport would not be a reasonable map to, like this object pi would not be a reasonable map from one to the other, because pi isn't trying to minimize distortion. Like it doesn't know that my arm can bend. It's just trying to move stuff not very far, right? So transport maps are perfectly happy to like tear things apart and then just glue them back together on the other domain. I see there, which is problematic. So like for instance, this paper from Jean Ferry and company had some clever tricks that use transport as a optimization cost within elastic deformation. So they say like, I have some subspace of deformations this hand is allowed to undergo, which makes sense physically, and now among those, I'm going to find the one that minimizes transport distance to register, which actually does make sense as opposed to the basic problem. Or Tim?
Yeah, I'm curious, like, because usually we have this constraint that the marginal projections, they are fixed, so essentially like we preserve the mass when we move. But for instance, like if you try to move, to map one volume to another, I guess we don't have guarantees that the volume is preserved.
100%. Yeah, volume preservation is another problem with transport. That one's a little easier to deal with. So there's an entire literature on what they call unbalanced transport, which is precisely this, that like your two marginals don't add up to the same value. So the formula, like this formula doesn't even make sense, right? Because pi would add up to different things depending on how you sum. So there are a lot of different ways to do it. One very simple thing, I keep picking up that nice piece of chalk and then putting it down in a weird place, would be to do the following. To just say, okay, I'm going to remove this constraint and just look at pi greater or equal to 0. And then what I'm going to do is add the KL between like the marginal, like that, and mu, and then the KL of the other marginal. I'm mixing discrete and smooth notation, but whatever. Like that. So like essentially, I'm going to take the row sums and then minimize their distance to the prescribed measure, rather than making these hard constraints that they're equal to each other. And so that's what most of these unbalanced transport things look like, is some balance between these two terms. Yeah.
So it means that like in the end we don't get exactly the output, we just like get something that...
Yeah, so if you solve this model, it means that pi is no longer a transport map. Like there's a lot less that you can say about it. There is a lot of nice theory out there. I think Lenay Chiza and some other folks, they're all French. All these French researchers have spent a lot of time proving theorems about many different variations of this problem. And this is a very popular one to study. In fact, there's even a variation of this Benamou-Bernier problem that does the unbalanced thing. In that case, I believe what you have to do is add, I think you need some term that allows, you kind of like add a term like this, like literally just a f of x t, and you like penalize f or f squared or something. So in other words, you allow mass to kind of evaporate, but then you want to penalize that, right? So if you pay me, I'm happy to send the references there. But yeah, that's called unbalanced, and that does solve that problem, but it does not solve the fact that transport doesn't know anything about rigid structure. It just knows how to like cut and paste stuff. Yeah, that makes sense. So optimal transport is often used as a cost function for optimization problems. I think one of the earliest examples, these days we think about generative models and GANs and so on, but actually the first example was in engineering. So here's one of the early ones, which I thought was kind of funny, which is in caustic design. This actually led to a startup out of EPFL that I think was quite successful. I believe it got sold to a jewelry company, if I recall, which did the following. So you take a generic beam of light that's like where you know the angle it's coming at, and then you have a piece of glass, like what you're seeing here, and you have a surface on the other end. And so you think of what's going on with I always confuse refraction through the glass here. It's essentially taking those light rays and it's like changing what direction they move in, right, depending on the surface normal of the glass. And so if you think about it, like there's some kind of mass conservation, in this case it's more like energy conservation, right, which is like you have the light energy going in here, and then when you move the rays around, you're like concentrating it at different locations, but it's conserved, assuming an ideal piece of glass here. And so they saw a really interesting, in some sense, just back propagation through a really nasty transport problem, where you prescribe an image on the wall, like Einstein here, and your variable is the shape of the piece of glass. And so what you do is you minimize the transport distance between the image of Einstein and the thing that comes out of your current piece of glass, and then you differentiate that through the geometry of this surface here. And what comes out is actually control over the shape of the caustics, which is kind of a fun, it's kind of interesting to think that this is one of the early examples of transport, because I think this is actually one of the harder things to differentiate through and be successful with, extremely non-convex. But yeah, and then you can 3D print that piece of glass, and what you get are these cool shapes. If you go to the EPFL campus, they have some, of course, it's Switzerland, so they have something called the Rolex Center, and right in the middle of that, they have a display which is built out of this thing. Yeah. In computer graphics, optimal transport is used for interpolation. So for instance, like maybe for you keyframe a density moving in time. These are not very impressive examples, but there are some out there. This is sort of my domain, so we've worked a lot on that, or extending it to like vector field data instead of just densities and so on. It's also used in like stippling and these sorts of problems. So like let's say that you have a black and white printer, but you have a grayscale photograph. Then a very typical thing that you have to do is find like the closest black and white approximation of your grayscale image, right? So maybe one way to do that is you view your black and white image as a collection of little pen dots. You can move those dots around, and you want to minimize the transport distance between that thing and the grayscale photograph that you input. And so in this case, the variables are the positions of these little black dots, and you're trying to minimize transport distance. So the optimization problem looks something like this. Like mu would be the photograph of the zebra. This is just a fixed constant. And then xi are like all the little positions of these samples here. And so this original work from Fernando de Goes and company was sort of the first one to show how to differentiate into this. They made they were using sort of compute. Oh, it's calling its cell phone. That's problematic. Wow. That's not good. Right, so, sorry, that's just very distracting. So that was the original application. It was constructed in such a way that like it really depended on solving this problem in the plane. Like he was using some fancy computational geometry here that we'll see later. Later on, it was extended in different ways. For instance, on the right-hand side, actually a former PhD student here at MIT showed how you can do this with like kind of random sampling style machinery. And so in this case, it was like I have some smooth probability distribution, like the posterior of a Bayesian problem, and I want to like generate some samples from it. So I like want to, the collection of 100 samples that best approximates this Bayesian posterior is exactly the same problem as the image processing one at the left, just in very high dimension. Sort of starting with that problem on the right, there's a whole set of statistical estimation problems that kind of fall into this domain. So we talked a lecture or two ago about the the maximum likelihood estimator, which we argued minimizes the KL divergence between your data and like a parametrized distribution, right? So like for instance, p theta could be like a Gaussian, and it's parameterized by its mean and covariance, and over all the possible mean and covariance, I want to find the one that best fits my data. Okay? So there's a different thing that was proposed in statistical literature that is called the minimum Kantorovich estimator, which is exactly the same thing, but now instead of minimizing KL, you minimize W2. And I think you can understand a lot of modern generative models through this lens, where like essentially the sort of schematic picture to have in mind is sort of drawn up here. You have the space of probability measures that like your model can do. So maybe you have a neural network, like a generative thing that makes this red region. You have your data set, which probably doesn't live inside of that space, and you're trying to find the closest projection of one onto the other. And there's been a lot of machinery over the years that's been developed for solving this computational problem, specifically given all kinds of different species of input data, like samples or the value of your distribution or what have you. So this is sort of the earliest machine learning / statistical application of these sorts of problems. And even before you jump to machine learning and generative modeling and diffusion, whatever, you can also ask all the same like college level statistics questions that you prove about MLE for the MKE. Like, what kind of estimator is this? If I have a finite data set and I approximate new data with this finite thing, is p theta a good approximation of the theoretical object that I care about? These are all reasonable questions. You can ask about bias and so on. And there's a whole statistical theory that's built around these objects here. Also in machine learning, transport has been used for domain adaptation. So I think the classic example here would be like, I go into my grocery store, I take photos of all the shelves, and I label all the cereal boxes. And now I take photographs in another grocery store, and I want to label all the cereal boxes there, but maybe there's a slight bias because like the lighting is different or something. So like somehow my data set is like slightly shifted between test and train. And so in this domain adaptation task, maybe what I want to do is like I train a classifier, like a model, on one space, and I want to kind of transfer it to another data set. Then for years, people have experimented with different optimal transport models that essentially compute a mapping from one data set onto the other, and then kind of borrow labels as a reasonable transfer learning strategy. There are many holes that you can punch in this kind of basic model here that have been addressed and people have thought about over the years in this transfer learning setup. And then the most modern kind of machine learning problems that study this stuff tend to be in generative modeling. So it's funny to look at these images now because when I first saw them, I thought, like, this is 2017, not that long ago. In my frame of reference, like, this was like super impressive, My machine learning model could generate these little itty bitty photographs of bedrooms. Of course, by today's standards, this is like, quaint. But once again, this sort of Wasserstein-Gann was one of the early generative models that was successful using neural networks. And the basic idea was to optimize a transport cost. So essentially, like, one of these would be your data set, the other would be your machine learning model for generating deepfake bedrooms. And really, this simple algorithm they write down here is nothing more than a numerical method for solving transport. One small detail, they are kind of forced to use the Wasserstein-1 distance, so this 2 is not there in their distance. That's for technical reasons, because that's an easier distance to evaluate, it turns out. It also doesn't have very good statistical properties, so there's a lot of effort to address that in later literature, like, can I optimize these sort of stronger notions of transport distance in the scan setting? And there's a really interesting empirical observation that, to my knowledge, is unsolved in this space, which is that people like me that are experts in optimal transport got so excited about this early work in GANs because we're like, fantastic, like finally we're relevant, like the state-of-the-art, generative adversarial network is using transport machinery. So like, cool, like we know all these neat tricks for making transport algorithms more effective and faster. We're going to start dropping them into this stuff and we're going to make state-of-the-art GANs. But the problem is that really didn't work. And there's some really interesting scientific questions hiding there. That in fact, the empirical observation over time after this Wasserstein-Gann paper, if you read that paper, there are a lot of, it's what's the right way to put it? Like, this is an empirically very successful model. At the time, it was like state of the art for what it was doing. But from an optimal transport perspective, it's far from state of the art. Like, it's doing all kinds of weird approximations that don't make a whole lot of sense in that theory. So a totally reasonable thing to do would be to kind of revisit this paper and improve that, right? Like, go back, we know all this theory, we know how to improve it, we know how to make this distance look like transport distance, and that's going to make it better. What we found is that there's actually an inverse correlation. And in fact, there's multiple survey papers that came out that tested this really thoroughly, and I think it's not understood at all, which is that the more work you go into improving the estimation of Wasserstein distance, the worse these things tend to perform. And to my knowledge, this is an open question that, like, clearly geometry is important for these generative models, whether it's this sort of transport thing in GANs or diffusion is sort of related to this in a certain way. That it's certainly true that these things are important. Geometry of the image space seems to matter. But apparently our model of geometry is not quite the right one. and so I think there's a really interesting question hiding here, which is just like, what do we do about that? Like, how do we reconcile these things? And what is the right objective function where if we actually make it smaller, these things perform better? And to my knowledge, it's just not understood. On the other hand, a happy byproduct of all that work, because GANs were popular, are much better transport solvers today in 2023 than there were like 5-10 years ago. So if what you care about is transport, you're solving these statistical problems, we can do pretty good at that. Okay, so as usual, we're talking too much. We won't get too far, but I thought I'd give you some little inkling into how these problems are solved in practice. Just like some pointers into the literature, and conveniently you already derived one of the algorithms in your homework, which is one of the more popular ones. But essentially the impression that you should get from lectures so far is that essentially there are so many different formulations of the transfer problem. There's like linear program, multiple linear programs, right? The primal and the dual. There's this fluid dynamical one. There's also other ones that like involve searching in the space of convex functions and all kinds of other stuff. And essentially, there's some kind of engineering that you can do. You can say, okay, at the end of the day, I want to solve a computational problem. And we've done this a lot in this class. Like, I want to compute curvature, right? So what do? I take my favorite smooth formula for curvature. I have like a triangle mesh sitting in front of me, or a point cloud, or whatever, and I'm going to try and make that formula work. The kind of interesting thing about this domain is that there's like a million different formulas for transport. And you might say, like, well, this is the domain I want to solve my transport problem on at the end of the day. And now I'm going to go back and choose a formula that's somehow convenient for that particular domain. And I think if you look at the computational transport literature, that's sort of what you see, is like a lot of like engineering where you can choose to discretize the formula that's going to make your life the easiest in the downstream setting that you're working with. And just like we've learned for Laplace operators and other things, there's no free lunch. What we'll see, the transport problem in theory with all these integrals has like 1,000 different beautiful properties, and that like when we try to make it work on a mesh or on a point cloud or on a data set, we'll be able to preserve some of those properties, but not 100%. Like maybe we'll get a triangle inequality, but we'll lose fluid dynamics, or vice versa. There's probably a nice version of this no free lunch theorem that could be proved in this domain. So I thought I'd mention a few different notions for discrete and discretized optimal transport that are popular in the literature. The first one you do in your homework, so we don't need to do in a whole lot of detail. But essentially what you hopefully learn from your homework is that if you take this basic problem and you just add to it minus the entropy of your transport map, this T here, then that unlocks this new algorithm for solving this problem, which is called Sinkhorn's algorithm, right? And if you did your homework correctly, what you found is a pair of formulas like this, which essentially show that solving this transport problem is nothing more than a bunch of matrix multiplies and then element-wise operations. So this is very efficient to implement in practice, where here this matrix K is nothing more than just exponent of minus your cost. Yeah? And so this algorithm, it has a long history. It goes back to the 1960s. And in fact, actually, when it was proposed, it wasn't for transport. It was just for taking matrices and making them doubly stochastic, like prescribing their rows and their column sums. And it's kind of interesting to read these old papers on transport because they don't realize it's connected to this convex problem, but they still are able to like prove that this algorithm converges. Like it's kind of interesting that way. Of course, these days the modern proofs are just showing that it's an optimization technique. But in any event, this algorithm was sort of rediscovered in the machine learning literature, arguably by our colleague Marco Cotturi, like maybe about 10 years ago, and it's led to this explosion of research in optimal transport in the machine learning domain, largely because you could solve it in 5 lines of code, right? That was essentially a big development relative to using expensive linear program solver. Moreover, as you kind of argued on your homework, at the end of the day, the expensive operation here is multiplying by this matrix K, but this thing is structured, right? It looks like convolution against a heat kernel, and so you can use that to make things even faster on certain domains, like meshes, right? Because we've now implemented heat diffusion on meshes many times in this class in different form. Now, there are problems with this particular model. For one thing, the optimal value here, if you think about it, so like let's say that I take a distribution and I just map it to itself, right? So P and Q are equal to each other. If I add entropy here, what I'm expecting is a diagonal matrix, right? In that case. But if I add entropy, that's not what you get. It gets fuzzy. And in fact, one thing you can show is for any non-zero positive choice of alpha here, you'll get a transport value even between two things that are the same that is positive. It's not zero when you have the same measure. So you kind of lose that distance metric structure that you might want. And so interestingly, what was proposed a couple years ago, which is really quite simplistic, like it kind of feels like a a boring hack, was the following. You're going to define this new quantity called the Sinkhorn divergence, where it's essentially entropy regularized transport. That's what this WCE thing is. And I'm just going to subtract off the diagonal, because this thing, if I put in the same measure twice, it's going to give me 0, right? Because it's just something minus itself. And the kind of interesting observation in this line of research is that this Sinkhorn divergence, this was proposed by Genevieve and company in 2016, it somehow debiases the transport distance. Like this sort of positive bias that it has goes away when you subtract. And moreover, this thing has some really nice properties. Like if you take a limit as s long goes to 0 or infinity, you recover well-known divergences between probability measures. So this is, I think, what people tend to do in machine learning literature. It's an easy fix to entropy regularized transport that makes it behave a lot better. But this is hardly the end of the story. There are many other ones. So for example, in fluid dynamics, you might have heard of the terms Eulerian and Lagrangian mechanics. So in Eulerian and Lagrangian mechanics, there's two very different perspectives on fluids moving around as a function of time. Right? So in Lagrangian mechanics, like if I have a tank full of water sloshing around, then what I'm going to do is track the position of every molecule as a function of time. Right? That's what Lagrangian mechanics does. A fluid is like a collection of particles, and what I'm going to compute are velocities and positions. And in some sense, you can view transport distance as a very Lagrangian theory, right? Like pi of xy is giving me where every particle went from one measure to the other, right? And what you can understand is when you convert this thing into the Benamou-Grenier problem, in some sense you've converted it into an Eulerian object, because J and rho are now functions of position, where the position remains fixed, and you're just kind of counting mass as it moves by. So you're like a little barnacle sitting inside of your tank of fluid sloshing around, just kind of like watching as physics happens. So that second perspective is called Eulerian. And so there's a whole set of Eulerian algorithms that try to discretize formulas like this one, and then use that to solve transport instead. So that leads to algorithms that don't look like linear programming, but instead are like these sort of discretizations of PDE. And there's a whole class of these things, dating back to the original Benamou-Grenier paper, that try to do that in a low-dimensional problem. And in fact, also in graph theory. So here's a kind of fun little graph theory exercise for all of you guys. If your cost for transport distance is just distance along a graph, like shortest path, then there's an equivalent formulation that looks like network flow. And so essentially, you can understand a lot of network flow problems as somehow analogs of transport solver on a discrete graph. And indeed, actually, this network flow problem, then you could actually translate back to a transport problem. And what you'll get is what is it called? It's called the Beckman problem, which is a formula for W1. Finally, there's one more class of transport algorithm I thought I'd mention, which is something called semi-discrete. Remember, this is the case where one of your two measures is composed of a bunch of points, and the other of the two is whatever you want. Right? And so here's the kind of interesting theoretical result in semi-discrete optimal transport. So here again, notice the semi-discrete structure says that one of the two measures, like mu, is composed of just a bunch of deltas at xi's, maybe weighted by a's. And then I really can't say anything about nu, like maybe it just has a density function rho. Then essentially what happens in optimal transport in the semi-discrete case is that you end up with like a little partition of the domain, which are all the places where like for each xi, this entire region of space is going to get assigned to xi in my transport map. That's the sort of theoretical result that you derive. And so you can actually show an equivalence between this problem and computing an object which is almost a Voronoi diagram. Like if you kind of glance at this blue thing here, it looks like Voronoi. But the problem here is that if I take, essentially what I want is if I take the integral over a Voronoi cell, I want it to equal the mass at a point xi, which doesn't happen a priori, right? Like the Voronoi cell might be big or small, depending on how close the x's are to each other. And so you define this slightly more general object called a Laguerre cell. And your variable is something called phi. So this is an object called a power diagram. Have we encountered power diagrams before? Probably not too many of you guys, maybe a few. So here's the basic idea. I have a bunch of points xi, like in the plane here. And I'm going to define a bunch of constants phi I. I'm going to say the Laguerre cell associated to xi is a set of all points y, so that the distance from xi to y is less than the distance to any other, exchange to y, right? That would be the Voronoi cell. But I'm going to bias distance by a constant, phi. Right? So when the phi's are equal to 0, I get the Voronoi diagram. Does this thing make sense? Maybe? Kind of? Nods? Some acknowledgement? Really? Anything like that? Yeah. Okay, good. What happens as I increase phi? Does my Laguerre cell get bigger or smaller?
Will they start to dissect?
What was that?
They start to dissect?
They can't intersect because there's an inequality here. Like this guy's Laguerre cell will start taking a bite out of somebody else's Laguerre cell.
Oh, it's on the both sides.
Yeah, that's right. So here, if I make phi really big, I'm making distances look small, right? So in other words, xi starts to look really close to more points, right? So as I increase phi, I'm increasing the size of this Voronoi cell, in effect. Does that make sense? And so essentially what you can show is that the semi-discrete transport problem, what it does is it optimizes for these biases, one for each xi, so that when I integrate my density over each Voronoi cell, I get the amount of mass at xi. This is kind of a weird optimization problem, but the good news is that it's finite. Notice that all I needed was for one side of my transport problem to be discrete, right? Because then I have this set of variables phi I, which are associated with the discrete things. And so that's the basic name of the game in this particular corner of the optimal transport universe. And from there, we don't have time in this course to cover these algorithms, but there are many. The simplest ones literally just do like gradient descent on these parameters phi. Right? So they look at like how much mass is in each cell, and they're trying to balance it to the prescribed value. And so you can you take the integral of rho in each cell, you see if it's the right value. If it's not, you decrease phi or increase it accordingly, and then you just iterate. This goes back a long time. Kind of interestingly, there's a weird intersection between numerical algorithms and computational geometry that happens here. Like this is a computational geometry problem. There's a discrete thing happening here. But people showed that one of the most efficient things you can do is actually just Newton's method for this particular problem for the phi's. And in fact, this is guaranteed to converge. So there's some nice convexity structure hiding here. And then more recently, people have done like stochastic gradient descent and so on. And in fact, there's some interesting applications here. So for instance, a couple years ago at the SIGGRAPH conference, they showed that you can use this to simulate an incompressible fluid. So here your fluid is kind of comprised of a bunch of particles moving around. And essentially, so hiding inside of here is this semi-discrete transport problem, which is kind of using things, is using one of these steps to advance your system forward in time. So here it's really, they're rendering the fluid as a collection of particles, but really the density is more like sitting in these power cells that are getting evaluated and evolved over time. I'm not sure how popular these fluid solvers are. I think not very. But it's an interesting perspective. It's somehow halfway in between particle-based fluids and grid-based. And it's fun to watch. Right, so there's all kinds of different algorithms out there that have all kinds of different advantages and disadvantages. Some of them are easy to implement, some are hard to implement. Some of them are efficient, some of them are slow, some of them are connected to different areas of math. And sadly, it seems to be the case that you just can't get it all here. I should note finally that actually, just in the last couple of years, machine learning has proposed all kinds of other algorithms that are also in this space and are useful, especially for kind of high-dimensional, like probability inference style problems. Probably the first really popular one was the Sinkhorn autodiff idea, where you literally differentiate into the Sinkhorn algorithm by just differentiating through all the iterations of this technique, which leads to some kind of tricky formulas and memory usage. But more recently, like, people have worked out, like, for instance, continuous versions of, so like, let's say I have two smooth probability distributions, and the only thing I can do is draw samples from either one, and I want an estimator for the transport distance between these two objects. And there's some interesting algorithms out there for how I can estimate that as efficiently as possible and without bias. Some of them try to solve like analogs of the Sinkhorn problem, for example, but in this infinite dimensional case, so I can never actually write down my variable. So point you toward this PhD thesis from Genevieve is a really nice read. Actually, she did a great job like articulating other problems and the math there. And then most recently, people use optimal transport plus neural networks. So for instance, maybe you parameterize either your like function pi up here as a neural network. Maybe you parameterize the Monge map. Remember, that's the thing that moves mass forward as a neural net. And now you translate all of your problems into that language and you optimize. And this seems to be the state of the art for high-dimensional problems. And plus, there's some interesting structure hiding in these problems that allows you to like engineer specialized neural network architectures that work well for this. So for example, the Monge map generically is the gradient of a convex function. And so there are these input convex neural network architectures that were proposed a few years ago that only know how to parameterize things that are convex. You can take the gradient of one of these and use it as your variable in a transport problem, and that's a perfectly okay thing to do. So there's an interesting literature hiding there. Finally, since we're almost done here, we'll note just a couple of interesting extensions and frontiers of these problems, and then in our next lecture we'll move on to a new topic. As always, like basically with any of the things at the end of this course, I'm just giving you pointers into like different parts of modern geometry that you might be interested in, and this is certainly one of those spaces. In optimal transport, there are all kinds of interesting problems that are derived. One of the simplest ones is to compute the average of a set of probability distributions with respect to transport distance. This is sometimes called a barycenter problem. So here you're kind of seeing what this looks like in one dimension. So we have three different measures, like the blue, the red, and the green guy. And one thing I could do is add up these functions and just divide by 3. But like if you look, each one of these is sort of peaked, maybe in one or two places. If I add them all together, then I'm just going to inherit all of the peaks from all of these functions, right? So for instance, here the red function is peaked on the left, the green function is peaked on the right. If I added them together algebraically, like on the right-hand side, I would just get a bimodal thing when I average them. But when I take their average in transport sense, it kind of slides horizontally along the domain. This problem finds a lot of different application. One of the interesting ones is in inference. So like in the Bayesian inference world, sometimes you have this problem, which is your data set is so big, you can't fit it on one machine. Right? So like I want a sample for my Bayesian posterior distribution. Like I observe people in this classroom's heights, and now I have some distribution over heights of humans that I want to sample from. That's conditioned on the data that I have. One thing I can do is take my data and separate it onto like 5 different computers and run inference on all 5 of those machines. The only problem is that then I get 5 slightly different biased estimators of my distribution. Then it turns out that fusing them together using transport distance is a nice model, that it has some nice statistical properties, which is called the Wasserstein subset posterior, or WASP estimator. And so this was proposed back in 2018, and it's been the object of study in some statistical work since then. There's a different question, which is like maybe I want to map between domains, but I want to evaluate like stretch rather than displacement, right? Like I want, when I map from one human to another, I would care more about distortion than I care about just like how far stuff moved. In that case, the transport solution of this problem is to move from transport distances to this thing called Gromov-Wasserstein distance, or DW. So usually notationally, rather than transport maps pi, they move to gamma as the transport map. And the basic idea is the following. I want a map that has the property that if x is close to x prime, and x gets mapped to y, then the image of x prime, namely y prime, should be close to y. Does that make sense? Notice that I never compute a distance from x to y. That's the difference between this and transport problem. Right, so this is saying I want maps that leave distance functions alone. Does that make sense? Math spiritually? So if I translate that to math, you get a formulation like this, right? So if x is close to x prime and y is close to y prime, then the distance between, like, or more generally, if the distances are similar, then the cost of mapping xy and x prime to y prime should be low when I multiply them together, right? That's what this is saying. Here's the problem, as you can. This is quadratic, right? The optimal transport problem is linear. This problem is going to be hard. This is a hard problem to solve. So sadly, this like small change in notation makes the optimization problem far less structured. Yes?
So we don't require to be the spaces to be in the same dimension, right?
That's right. Yeah.
And before we had to be in the same dimension?
That's right. So the transport problem, you have like 2 different Gaussians on the same space, and you're trying to align them to each other. This is like I have one object in one space, another object in another space, and I just want a map that kind of preserves the distance function. Yeah. This is used a lot, like it's used in a lot of shape matching tasks. But the reality is that the algorithms here are heuristic. Like this is an NP-hard problem, and you're doing gradient descent and hoping for the best. This is a very different scenario. Other things people do in transport are gradient flows. So gradient descent in the transport distance metric has a lot of nice properties, and it turns out that a wide class of partial differential equations can be written this way. So like for crowd simulation is the image that's being shown here. Actually just recently, like literally in the last year, people have used this now to solve a lot of inference tasks in very high dimension. They show that like Fokker-Planck equation and some other things that show up in statistics are very cleanly described in optimal transport language, and some of the state-of-the-art solvers in that domain come from this literature. A different question you can ask might be, can I apply transport to data that isn't just a probability distribution, like our Tim asked about unbalanced stuff? You could also ask about like tensors or vector fields. Like what would it mean to animate a path in the space of vector fields? And there are some works out there that try to study these problems. The basic challenge in this domain is, what is the analogy of mass conservation? It's not so clear anymore. Like what should be the object that we used to call a transport plan pi is now not so obvious, right? Because like, how do I add up vectors and get something prescribed? And then finally, there's a lot of probability problems hiding here too, right? So like, if I have sample access to two measures, can I compute sampler that samples from the Wasserstein barycenter, for example, is kind of an interesting algorithms question and one that people continue to study. So in any event, that was your whirlwind lecture and a half introduction to this little corner of geometry research. With that, I think we'll leave this behind, and in our next couple lectures, we'll be talking about correspondence mapping problems. So like, given two pieces of geometry, how can we map from one into the other, given different assumptions on what that map should look like? So with that, everybody have fun writing your project reports. I look forward to very quickly glancing through them once you turn them in, and I will see you all on Thursday.